Hello. All right, so this is fantastic. All right, so let's review the chain rule from last time. So if you have f of g of x and you want that derivative, I think we got to go back to blue. Sorry. Then this would be f prime of g of x times g prime of x. And remember, what you need to do is isolate the inside function and the outside function. And the chain rule says that the derivative of this composition would be the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So for y is equal to 9x squared plus 4x minus 2 to the 6th power, we would say that y prime is equal to, and then we would isolate the outside function. That would be x to the 6th. You're raising something to the 6th power. So we would use the power rule. So that would be 6 times some stuff raised to the 5th. The stuff that gets raised to the 5th is the inside function, unchanged, times the derivative of the inside function, which is 18x plus 4. Okay. I think we also did example 4. This would be the derivative of the square root function, which would be 1 over 2 square roots of, and then you evaluate that at the inside function, times the derivative of the inside function, which would be 8. 8 and 2 simplify to give us 4 over square root of 8x minus 3. And did we do example 5? Yes. So this one would be y prime is equal to 1 over 2 square roots of 1 minus x squared times the derivative of the inside, which is negative 2x. The 2's cancel. The negative goes either on top or out in front. And it's negative x over the square root of 1 minus x squared. All right. So that's where we pick up today. We want the derivative of x times 3x squared plus 7 raised to the 4th. Overall, what kind of function do I have? Okay. What operation is going on here? Product. We have a product. We have the x right here. That would be sort of the f. And then this other part here, the 3x squared plus 7 raised to the 4th, that would be the g. So overall, I have to perform the product rule. So we're going to have y prime is equal to the derivative of the first one, which is 1, times the second one, unchanged, plus the derivative of the second one. Well, the second one is a power. So, and we have stuff that's on the inside that's non-trivial. So I need to use the chain rule in this. So the derivative of 3x squared plus 7 raised to the 4th would be, to bring the 4 down, leave the inside alone, decrease the power by 1, and multiply by the derivative of the inside. The derivative of 3x squared plus 7 is just 6x. And that piece alone is the derivative of the g part. Then we still need to multiply this by f, which is x. Now, when we go to simplify something like this, we don't necessarily multiply everything out, but we try to get it into a factored form. You'll notice that I have 3x squared plus 7 and 3x squared plus 7. They're raised to different powers, so I can factor out some of them from both pieces here. So how many 3x squared plus 7s can I factor out? I can factor out 3 of them. On the left piece here, that leaves me with 1 3x squared plus 7. on the right, it leaves me with 4 times 6x times x, which is 24x squared. Like so. And we just simplify this inside. And that would be 27x squared plus 7. And you can use regular parentheses if you want to, whatever. Questions?
How did we get from 3x squared plus 7 to 4 to 3x squared plus 7?
This piece right here, this is the derivative of 3x squared plus 7 raised to the 4th. So we bring the 4 down, the inside stays the same, the power decreases by 1, and you multiply by the derivative of the inside. So this piece right here is the derivative of that piece. Yeah, this thing that I've underlined in red is all one thing.
Can you kind of explain again the logic of how you got to that first line of y prime equals something?
This one?
Yeah.
We use the product rule, and we know that we have a product of 2 factors. We had x times and then all this other stuff. So we have to use the product rule. So it's f prime g plus g prime f.
So then where did all this stuff about chain rule?
So just like the product rule or the quotient rule, you use the chain rule when it is necessary, all right? So the question is, the g that I formulated here, what form is the g in, and how do I get its derivative? Well, g is something raised to a power, so I need to use the power rule. The something is not just regular x, so I have to use the chain rule.
Can you maybe write out the equation like in symbols or something of how you did that? Like I still don't understand. Like I wouldn't be able to put that into it. I wouldn't be able to.
Let's see. Do you know that this whole thing that's underlined right here is the derivative of 3x squared plus 7 to the 4th? All right, so maybe I could write this for you. That this piece right here is equal to the derivative of 3x squared plus 7 to the 4th by the chain rule. Let's see here. What about this right here? This is f prime g plus, all of this is g prime f. How's that? Is that better? That's what you're looking for. Yeah.
That's for g prime and just the chain rule. That's the only time chain rule is.
Yes. Yeah. But the overall arc here is the following. It's that you use chain rule or product rule or quotient rule whenever it comes up. So every time you need to take a derivative, you evaluate what you have and what you need to take that derivative at that moment. That's exactly it. Yeah. So sort of recapping, like the first piece of this was x. You need to take the derivative of x. So what do you get? You get 1 and you're done, right? Okay. Then the g is by itself. Then you needed to take the derivative of 3x squared plus 7 raised to the 4th power. How do you take that individual derivative? That is the chain rule. Yeah. So you have to sort of bring these in whenever you need them. Okay. Other questions? Okay. All right. I feel like I want you to do example 7. I'll give you some guidance, maybe. On example 7, we have x plus 2 to the third power times 2x plus 1 to the fourth power. So what overall rule are we going to use to find this derivative? Product rule. What is f? Yeah, this piece right here is the f, and this piece here is the g. Now, to take the derivative, you'll need to use the chain rule as necessary. Okay, go ahead and work that with your partner. Oh, you had to. Oh, okay. Yeah. You can do it at the same time. Is that right? Yeah, this is the unchanged function. So this is the derivative of the f times g unchanged. Oh. Plus c prime times f unchanged. Yeah, this one is involved, right?
So it has to be the quantity inside substance.
Because if you have a binomial like x plus was it 2, you cube it, you get the 4. Raise it to the fifth power. Well, weird. You still only have 2 terms. So that's it.
16 minus 2.
Did you factor out those two common ones?
Yeah, like I have the exact same thing as you. Minus I wrote 16 to 19, but that was just me not writing the right thing. And I think that's right. I just don't know.
Okay, let's check it. Let's see if it works. Okay. All right. So we're going to have y prime. We're going to use the product rule. And the derivative of the first one is 3 times x plus 2 squared times 1 for the derivative of the inside times the g function unchanged, plus the derivative of the g, so it's 4 times 2x plus 1 cubed times the derivative of the inside, which is 2, times the f function unchanged. And now what you look at is the two individual pieces that you have here. You have the first part, you have the second part. And you look to see what the most you could take out in factors from each of those parts would be. First off, I notice that I have x plus 2 squared and x plus 2 cubed. So that means I can take out squared. All right, so it's x plus 2 squared. Squared. And then I look and I see that I have 2x plus 1 to the 4th and 2x plus 1 cubed, which means I can take out the cubed version of that.
I don't understand why you can take out the lesser one. Because the 4 is on the outside and the 3 is on the outside of this one.
It's the powers. And you can only take out as many as they both have.
Okay.
Right? So you think of the left one has 4 terms that are 2x plus 1. The right one has 3 2x plus 1s. So I can only take out 3 of them.
I was going to say addition, so I always want to add them together.
Uh,
And you can't add them to figure out the powers, is what I think.
Right.
Okay, I got it.
Yeah. No, we're actually sort of dividing, if anything. Yeah. So, but now you determine what's left over. So what would be left over in the left term would be a 3. The x plus 2 squared is gone. The 1 is irrelevant. And of the 2x plus 1 to the 4th, I took out 3 of them. So there is 1 remaining. Plus. And now on the right side, I have a 4 and a 2, so that's an 8. Of the 2x plus 1 cubed, I took them all out. Of the x plus 2 cubed, I took out 2 of them. That leaves me with 1 of them. And then we just simplify this this inside here. Okay. So the first parts here stay the same. And what are we going to get here? 6x and 8x is 14x. And 3 and 16 is 19. Is that right? And voila. Questions?
Okay, so you said that you took out like 3 of the 2x plus 1s, but why on the outside of the brackets is there? Is that like where it went?
Mm-hmm.
You took them out?
Yeah, what you really, the skill that you have to really work on here is you have to sort of visualize 2x plus 1 as a single item. So if this were like, right here, we're going along here, this would be like a to the 4th plus blah, blah, a cubed. Well, then how many a's could you take out? If you had a to the 4th and a cubed, you would take out a cubed. Right? Well, it's just the a is a little bit more of a bigger unit, right? So you have to sort of think of it that way. That's the way I look at it, at least. The parentheses sort of denote larger type items. Okay, why don't you and your partner give number 8 a go? Now, what is, first off, identify the outside function. The quotient is the inside function. What is the outside function? Yeah, it's a fifth power deal. Yeah. Yeah. So, did everyone see that the fifth power is the last thing that would happen in evaluation? That makes x to the fifth the outer function. So you basically want to use the power rule, chain rule version on the fifth part. Okay, go. Let's see if you can do it. The first thing you do is the derivative of x to the fifth. Type deal. You need to treat the inside as a single unit. Okay? So it's going to go outside that.
Okay.
So not
One
just
of them.
the,
It's not going to go outside both of them, though, just one of them.
because the inside should be treated as one thing.
Okay.
Yeah. So you want to take the derivative of the x to the fifth, which would be the inside. And then what power is outside? Right? So how do you take the derivative of and now change the derivative. Okay, right next to the markers. Are you happy? Okay. Okay, that's what you did. Is that it? 5x? That's what you this said, when you talk about the 5x to the 4th, you're sort of modeling that over the whole thing. So it's the 5 comes in front, then the inside, then the 4th. Okay, let's check it. Let's see what we got here. All right, so the thing to notice here is that it's something raised to the 5th power, ultimately, right? So to take that derivative, we're going to use the power rule. So it's going to be 5 times the inside unchanged, lower the power by 1, right? Now we're going to invoke the chain rule, so it's going to be times the derivative of the inside. Well, the inside is a quotient, so we need to use the quotient rule. So it's the derivative of the top times the bottom unchanged minus the derivative of the bottom times the top unchanged divided by the bottom squared. Okay. Now there's a few things that we can do to this. Let's try some of them here. This would be 5 times x plus 6 to the 4th times 3x minus 2 minus 3x minus 18 divided by 3x minus 2. And now the power on this, notice from the left piece, there's a power of 4. From the right piece, we have a power of 2. That gives me a total power of 6. 6.
Where did you get 3x minus 2 minus 3x minus 18?
Distributing this negative 3. Did I do it right? Yeah. 1 times that. Minus 3 times x plus 6.
And the 6, the 6 power on the bottom, that comes from 4 and 2.
Is this one? Yeah. And then one last thing to do here. The 3x, those cancel. And that leaves me with minus 20. And minus 20 times 5 is minus 100. Questions? Okay, I'll give you a moment to write that down. Okay, let's look at example 9. Example 9 says the area A of a circle with radius r is A is equal to pi times r squared. The radius r of a circle with diameter d is r is equal to d over 2. Right? Radius is half the diameter. Write a composition function of A as a function of the diameter d. Then find the rate of change of area of the circle per unit change in diameter. All right, so basically we have the following. We have A of r, right? So I can write the area of the circle as a function of r, and that's what's given to me here. So this is pi times r squared. And I can write the radius of a function, the radius of a circle as a function of d, which is d over 2. I can combine these so that I can create an area function that goes straight from knowing the diameter to knowing the area without having to go through the radius. Okay. All right. So this would be A of r of d. right? This is that composition. You can also think of it as A composed with R of D, right? If you wanted to do it that way. So this would be A of, and we're going to insert the formula for the radius, which is D over 2. The D over 2 then acts as the radius and goes into the area formula. So this would be pi times D over 2 squared. And if you simplify that, you get pi D squared over 4. So that is the area of a circle, not based on the radius, but in fact based on the diameter. Okay. Next, we're asked to find the rate of change in the area based on a change in the diameter. So I'm going to do this sort of the way you expect. All right. The area based on the diameter would be pi d squared over 4. So A prime of d would be 2 pi d over 4. Now, don't get caught up on this. The only variable here is d squared, and the derivative of d squared is 2 times d. The pi and the 4, those are constants, and they just hang on for the ride. But I can simplify here, and I can get pi d over 2 when I cancel off 2 and 4. Okay? So don't get too upset with the variables here. The only thing going on here is d squared, and the derivative of d squared is 2d. Okay? No, it's part of a constant. You think of the constant as being pi over 4. Yeah. So, yeah, no. You only need to invoke the quotient rule when you have variables in the quotient.
I'm talking about how constants, derivatives don't zero.
You could actually do the quotient rule, but it would annihilate a complete half of that. Yeah. So by being 0. Yeah. All right. Now that was the old school way to do this. How does the chain rule work in this instead? Okay. So if we wanted to do the chain rule, right, we would have A of R of D, and then the chain rule would say that that would be A prime evaluated at R of D times R prime of D. And what would that give us? Well, first, note that A prime of R is 2 pi times R, and the R in this case is the function R of D, which would be D over 2, times the derivative of R of D. Well, the derivative of R of D is just 1/2. You can really think of this as 1/2 D, and so the derivative of that is 1/2. And then when you work this out, what do you get? Well, this 2 and that 2 cancel, so this is pi D over 2. It's the same. All we're doing here is verifying, number one, that the chain rule works, and that you can get the same results. Let me finish this example up here on the bottom so that you have homework. You do have homework due on Wednesday, so you have to get it done. All right. Example 10 is the sides of a square are expanding so that after t seconds, the side length is x is equal to 3t plus 1. Find the rate, the area of the square is expanding after t seconds. Okay. So let's create a function of the side of a square giving me the area of the square. So this is auto-saving. There we go. So a of x is equal to x squared. That's the area of the square. Then we have a function that tells me how large the side is after t seconds. So after t seconds, the side of the square is 3t plus 1. Now, another formulation for the chain rule is the following. Ultimately, we want the derivative of the area with respect to time. Now, this is the Leibniz sort of fractional notation. This is one of the benefits of the fractional notation. The chain rule formulation with the fractional notation would be the derivative of this first one, so it's dA dx, because it's d of the function divided by d of the variable, times the d of the function divided by d of its variable. Well, that's dx dt, and what happens sort of algebraically to the dx's? They cancel, leaving you with the dA dt. This gives you a formulation way of showing all this stuff at work. So the derivative of dA dx would be 2x. Now we have to evaluate that at what x is, which would be 3t plus 1, times dx dt. Well, the derivative of the x function over here is just 3. So this would be 6 times 3t plus 1, which is 18t plus 6. And then evaluating this at t, evaluating this at t equals, what do we have here, 5? We end up with 18 times 5 plus 6. And the appropriate units are, it doesn't say how big the square is. Let's just say it was inches or whatever, inches per second. Or units. You could put units per second if you wanted to. Okay. Do not concern yourself with this. This is just the notation that says take this function and plug in a 5. Okay. Do y'all have the homework from last time? I need to put that up on the big screen. You don't have it. Okay. All right. This is due on Wednesday, so let's get it done. Office hours today at 2 o'clock if you need help. Have a great day.